For some reason, this chain rule causes some students to be, let's say, tight, tense, I don't know, not relaxed. So before you watch this, meditate, calm down, relax. It's not difficult, it's just scary, but for no good reason. Okay, so what's the chain rule? The chain rule tells us how to take derivatives of compositions of functions, right? That's the chain rule. Now, when our functions were single variable functions, so f was a function from R to R, and g was a function from R to R, their composition was a function from R to R, and the chain rule was, in fact, not very complicated, right? The derivative, so in single variable calculus, the derivative of f of g of x prime was, who can tell me? Right, take the derivative of f evaluated at g of x, great, and then multiply it by g prime of x, which we called the inner derivative. Right? Everybody remember this? This is precisely what's going to happen for compositions of functions of multivariable. Okay, more variables. And it's precisely what's going to happen, just the formulas are going to look a bit more involved. Okay? But we're going to do examples, and you'll see that this is precisely what's going on, and there's no reason to be scared. And in fact, there's no reason to try to memorize the formulas. If you understand that that's what's going on, that's precisely what's going to happen. Okay? So let's write the first theorem. I'm going to mention two theorems, but you can actually write a theorem for every possible composition. So let fxy be a C1 function in a domain D. Okay, so we're looking at good functions. Okay. And let x of t and y of t, note that these are single variable functions, be differentiable in the single variable sense. They have derivatives, x prime t and y prime t, on an interval, which we're going to call I for interval, D for domain, on an interval I, such that we can compose. Whenever we discuss composition, or anything related to composition, like taking derivatives of compositions, the chain rule, composition requires that the domain of the function you're composing with has to include the range of the function you're composing with, right? So the range of g has to be included in the domain of f, so that f can operate on g, right? So that's what I'm going to write now. Let x and t and y of t be differentiable on an interval I, such that for any t in I, the point x of t, y of t, takes you to the domain of f. And what I want to do now is have f operate on this. That's the composition. Okay? Define, here's the composition. We're going to call it big F. Big F is going to be a single variable function, f of t. What is f of t going to be? It's going to be take t, x of t it, y of t it. Now you're getting a point in D. D is the domain of f, which is a two-variable function. Have f operate on that point. Do you see a composition here? Does everybody see that this is a composition? Do you see that it's well defined because of this requirement, that for every t, this lands in the domain of f? Good, everybody? Okay. So this is still not a theorem. This is just a lot of blah, blah. Now we want to write the theorem. The theorem is going to be the chain rule. What's the derivative of f, capital F, with respect to t? Okay, then df to dt, or you can write f prime of t. Note that these are good old regular d's, because this is just Leibniz notation for single variable derivative. Okay? This is a function of a single variable. Do you see that? So this is its derivative with respect to its only variable. You can write f prime of t. The reason I'm writing like this is that it's going to fit in more nicely with what's going to be written here and what's going to be generalized later. Okay? So df to dt is, so I'm not going to look at my notes. I'm not going to look. Let's think. Okay? I want to do a chain rule. So what does the chain rule say? Take the derivative of f. Wait. What's the derivative of f? F is a two-variable function, right? Partial derivatives. Good. Take the partial derivative of f with respect to x, multiply it by the derivative of x with respect to t. Then take the partial derivative of f with respect to y, multiply it by the inner derivative, the derivative of y with respect to t. And the theorem tells you add them up. Okay, clear? We're not going to prove these theorems. Their proofs are, they get a bit, it's somewhat of work, and we're not going to spend time on it. But let's write. So I just have to be careful with the d's. Remember, the squiggly d's for multivariable, regular d's for single variable. So it's going to be the derivative of f with respect to x. This is a partial. Evaluated at x of t. I don't want to write it because I want the formula to be short and precise. But it's evaluated at x of t. Right? Times dx to dt. Plus squiggly, derivative of f with respect to y, that's the partial with respect to the second coordinate, times dy to dt. Do you agree that this is chain rule-ish? Outer derivative times inner derivative. Two variables do both. Clear?
The sum.
Example?
No, the sum.
Why the sum? You're asking me for some, I don't have a geometric insight to answer that. It's in the proof. It's easy to see why that happens, but good question. Bad teacher, no good answer. Okay, so let's do an example. Let's do a quick example. In fact, the proof follows from using the definition of differentiability. And that's where it stems from, okay? You have the A times H, but without actually doing the proof, for me, it's hard to give you a good answer. Let's do an example. So what do I need in an example? I need to tell you what f of xy is, and I need to tell you what x of t is and what y of t is, and then we're going to compose and do the chain rule, okay? So f of xy is going to be the function x squared y minus y squared. And then x of t is just going to be t squared, and y of t is going to be 2 times t. So these are the ingredients. This is what I want to compose. And I want to compose. I want to do what f of x of t, y of t, and find its derivative. Okay, so remember, f of t is by definition little f of x of t, y of t. And we want to find f prime of t. That's what I want to find. The derivative of this function with respect to t. I'm just going to do chain rule. So what does the chain rule tell me? Take the derivative of f with respect to x. What is that? 2xy. Do you agree? Okay. And I have to evaluate this at x of t, y of t. Okay. Note, by the way, the partial derivative, this is df to dx. The partial derivative is a function of both variables. Okay, that always happens, except when it doesn't. But those are specific cases. But in general, the partial derivatives are again functions of both variables. Okay, so I have to evaluate this. I'm going to have to plug in. I'll do that in the next step. For x, I'm going to have to plug in t squared, and for y, 2t. Right? We'll do that in the next step. Times the inner derivative. What's the inner derivative? X prime of t. What's x prime of t? 2t. I don't need these parentheses. 2t. Plus, do you agree? df to dy. What's df to dy? X squared minus 2y. Right? Again, look, the function, the partial derivative is again a function of both variables. Good? Times the inner derivative of y with respect to t, 2. Do you agree? Okay. Now, recall that the outer derivative is evaluated at the outer point, right? So I have to plug in t squared for x and 2t for y. Okay? Everybody with me? So I get 2 times t squared times 2t times 2t. This is the y and this is the 2t from here. And here I have x squared, so it's t to the power 4, minus 2y minus 4t, and all of this multiplied by 2. Do you agree? And now I just have to figure all this out. So what do I have here? I have a t to the power 4 times 2 times 2 times 2. That's 8. So it's 8t to the power 4 plus 2t to the power 4. That's 10t to the power 4 minus 8t. Good? Now this is an easy example. And in fact, we worked way too hard to solve it. Why? Since all the functions here are very concrete, which is not always going to be the case, but since all the functions are very concrete, I can actually calculate what capital F of t is before I take the derivative. Okay? Are there questions so far? Okay? So here we just found the derivative using the chain rule. But note, maybe we'll use a different color. So here we use the chain rule. Chain rule. The previous theorem I didn't write, but that's the chain rule, of course. But note that this equals, what is f of x of t, y of t? It's just putting x of t here and y of t here. That's the composition. Do you agree? So what is it? X of t is t squared, and then I have to square it, so it's t to the power 4, times y, times 2t, minus y squared, 4t squared. Do you agree? Do you agree that that's the composition? And it's, of course, a function of t, obviously. And what is this thing? This is 2t to the power 5 minus 4t squared. Good? And now if I want to take the derivative of a function of a single variable, polynomial, I know how to do this. The derivative of this is 10t to the power 4 minus 8t. Good? So when everything is explicit, you don't really need the chain rule. Just compose and take the derivative. But this is going to work even when things are not explicit. And we're going to make extensive use of functions which are not explicit and are called implicit functions. That's a topic coming up shortly. Clear? Everything good? Okay. Now I want to write again the chain rule, but this time I want to write the chain rule for a composition where both the inner and the outer functions are functions of two variables. Okay, here the inner functions were functions of a single variable and the outer functions was fxy. So here's the chain rule again. Here's another version of the chain rule, and there are several. I'm just going to write these two, but you can, if you get the idea, you can understand how to do chain rules even without stating the specific theorems for every possible case. So now we're going to have fxy, a function of two variables, x of u and v, and y of u and v. All of them I'm going to suppose there's C1. Okay? And I'm not gonna state precisely what the domains are, but I'm going to assume that they compose nicely. Okay? And define, so assuming they compose nicely, I'm going to define capital F, but capital F is now going to be a two-variable function of u and v to be take little f of the x-coordinate is going to be x of uv, and the y-coordinate is going to be y of uv. So again, this is a composition, but this time both the outer function and the inner functions are all two variable. Clear? Okay. If you want to state it precisely, you have to state that uv are in some domain in R2 such that the range of x of uv fits in the x-coordinate of the domain of f, and the range of y of uv fits in the y-coordinate of the domain of f. So, well, actually, both should simultaneously fit in the domain of little f. Good? Okay. And now, how many formulas am I going to write now for the chain rule? Why 2? Because I'm going to have one formula for the derivative of f with respect to u, and one formula for the derivative of f with respect to v. And each one is going to be chain rule-ish. Take the derivative of f with respect to x times the inner derivative, plus take the derivative of f with respect to y times the inner derivative. Okay? Again, I'm going to put my notes aside, and let's see if we can do it. So the derivative of f, capital F, here everything is going to be squiggly d's. Okay, everything, because it's all partials. There are only partial derivatives in this context because it's all two variable functions, right? So the derivative of f with respect to the variable u equals the derivative of little f with respect to its first variable, x, times the derivative of x with respect to u, the inner derivative, and I'm looking at u, plus the derivative of f with respect to its second variable, y, times the inner derivative there, the derivative of y with respect to u. Good? And the other formula, the derivative of f with respect to its second variable v, capital F, make sure your f's look different. Okay, that the big f's are squarish and the little f's are roundish, or the big f's are big and the little f's are little, or somehow don't get confused. Okay, so the derivative of f with respect to v is the derivative of little f with respect to its first variable x times dx to dv plus df to dy times dy to dv. Then, so this is the chain rule for composition of two variable functions, three two variable functions. Good? Let's do an example of this. Let's do another example. Maybe I don't need to erase, I have an empty board there.
The answer is different.
Hmm?
The answer would be different.
What do you mean the answer would be different?
Like for the two chain rule.
It could happen to be the same, but in general it's derivatives with respect to different variables. There's no reason for them to be the same. Okay? Okay, so let's do an example. Again, I'm going to do an example in which you can solve without the chain rule. You can just go ahead and compose and take the derivatives, but I want to do it using the chain rule, and then we'll check ourselves the short way. Okay, so here are the functions. F of xy is going to be e to the power x squared y. And x of uv is going to be the root of u times v. And y of uv is going to be 1 over v. Okay, so we have rational functions and roots and exponentials and powers. We have a lot of fun going around. Okay? So let's find, so we're composing. We're plugging in this for x and this for y. We're getting a function of u and v, and we want to find the derivative. Okay? So let's write f of uv is little f of x of uv, y of uv. And I want to find the two partials. So what is df to du? So I'm going to take the derivative of little f with respect to x, So it's what? E to the power x squared y times the inner derivative. Note that I'm doing single variable chain rule to find the derivative of f with respect to the variable x here, right? So it's e to the power x squared y times 2xy. Do you agree? That's df to dx. Does everybody agree? Times dx to du, the inner derivative. What's the derivative of x with respect to u? So this root v is just in the way. It's the derivative of root u. The derivative of root u is 1 over 2 root u. Good? Plus, if you're feeling overwhelmed because you don't remember how to take partial derivatives and single variable derivatives, then meditate and do it slowly on your own. But you have to know how to do this. Okay? This is, of course, important and basic. We're going to do it all along the course. You have to know how to take derivatives. Okay, plus the derivative of f with respect to y, so it's e to the power x squared y times the inner derivative here, which is x squared, times the derivative of y with respect to u. So the derivative of y with respect to u is what? 0. Y is un-u-ish. Okay? So let's continue this. This entire term is gone because of this 0. And here I have to plug in x of uv for x and y of uv for y. Okay, so what do I get? So x squared is just u times v, right? Y is 1 over v. So x squared times y is just u. Do you agree? So this thing becomes e to the power u times this 2 here, times x, which was root of uv, times y, which was 1 over v, times root of v, times 1 over 2 root u. And now things should cancel out. The root u, well, the 2 and the 2 cancel. Do you see that? The root u and the root u cancel. The root v and the root v become a v and cancel with the v. So, c'est la vie, all that remains is e to the power u. Do you agree? Beautiful, huh? Wonderful. Okay, the next one is going to be even more cancel-ish. So let's do df to dv. Did everybody follow what I did? Okay. Do you agree that it's not scary? It's really just chain ruling along. Okay? Do 3 or 4 of them and you get the idea. Really. Really, really. There are some places in this course that are challenging. Okay? Some integrals we're going to encounter along the way, I don't know, surface integrals. You have to know how to draw things and you have to think a lot. This is really straightforward. Okay? Do 3 or 4 of them and that's it. Good? Everybody feel confident? Okay. Let's do df to dv. So I need f with respect to x, but I already calculated it, so I'm just going to copy. So it's e to the x squared y times 2xy times dx to dv. Dx to dv is root u times 1 over 2 root v. Do you agree? Plus d little f to dy, which I also calculated already. So again, I'm just copying. E to the power x squared y times x squared times the inner derivative. So now it's the inner derivative of y with respect to v, which is negative 1 over v squared. Do you agree? Okay. Now I have to plug in the x and the y. For x, I have to plug in root uv. For y, I have to plug in 1 over v. Right? Let's do that. And at first glance, it looks more complicated because nothing cancels. In the first derivative, this entire term canceled. So this I already did. So I know this is e to the power u times 2 root uv times 1 over v. And then I have this business. Root u times 1 over 2 root v. So that's the first expression, plus e to the power x squared y is still just e to the u. X squared is root uv. And then I have, well, this becomes a minus because of this minus. And then I have 1 over v squared. Good? And now let's see what happens. So
X squared become just uv.
x squared should become just uv. Thank you very much. You're right. Good? Everybody? Okay, so let's see what happens here. Here I have one of the v's canceling out. So I have e to the u times u over v. Do you see that? So all this expression is e to the u times u over v. Right? What about here? The 2's cancel. The root v's from here and here cancel. Root u times root u is u divided by v. So this thing is also e to the u times u over v minus e to the u times u over v. So this thing is in fact a very deceiving way of writing just 0. Good? Is the chain rule clear? Now, as we did in the previous example, I claimed that we could have gotten these two answers much faster, directly, if we just plugged in everything into the definition of capital F. So what do we have? We have e to the power x squared y. What is e to the power x squared y? We already calculated it. X squared is uv, y is 1 over v, so x squared y is just u, so e to the power x squared y is just e to the power u. Do you agree? What's the derivative of this with respect to u? What's the derivative of this with respect to v? 0. Huh? Good? So we did it correctly, I agree. We did it the long way. This is kind of shorter, but this is just an example to practice chain rule, and here we can actually check that what we did is, well, correct. Okay? And an important thing to pick up along the way is the fact that partial derivatives are also functions of both variables. Okay? That's one of the most common errors in this course. People thinking that df to dx should be a function of x, and df to dy is a function of y. And you're saying, well, of course it's not. But then you get to more abstract arguments, and you write things like that, and everything following from there is completely false. Okay? So note, partial derivatives are always have both variables in them. Okay? Good? Everybody? Okay. So this wraps up our discussion of the chain rule, and you need to practice. It does require some practice in order to get a good feeling about it, okay? But it's not difficult. It's really very straightforward, okay? Don't try to memorize the formulas, because then it really gets kind of scary. Just understand the idea. You don't need... when I did this, I never looked back at the formulas. Not because I memorized them, because I understand what's going on. The derivative of this with respect to this times the inner. Okay, good? Great.